That there would be one time on a quiz you would have to calculate standard deviation. That was it. You do not have to do that on a quiz again. That will not be on an exam. I will not expect you to calculate that kind of a formulaic standard deviation again. Any other problems that deal with knowing standard deviation, I will give you that value, or it will be readily available to you on your quiz. Okay? All right. Now, to finish up with the spread stuff, we have one special type of distribution that we're going to look at. And with standard deviation, again, remember standard deviation is a measure of spread. And for certain types of distributions, this measure of spread actually tells us a very large amount of information about the data that we're collecting. And the kind of distributions that standard deviation becomes very helpful with are what are known as bell-shaped distributions. Bell-shaped distributions are distributions whose pictures look sort of like a bell. They have this sort of bell shape to them, something that looks roughly like that. That's what a bell-shaped distribution is. Okay? When we're dealing with bell-shaped distributions, there's a lot of properties, a lot of shape information we can get about this. First thing you notice about this graph is what? What kind of shape does this have besides the bell shape? It's symmetric, right? In identifying that, we know, or we are told now, that the mean is going to occur right there at that peak in our bell shape, the mode of this graph. Okay? Further than that, when we can identify standard deviations for distributions that look like this, that gives us a lot more information. Okay? Let's start by going back and looking at some data that we've worked with before. It's up here. Okay, and we're going to look at the football touchdown data stuff that we had earlier. If you graph this, can you hit that light box for a second? If you look at this distribution, if you were to graph it using the, I guess I'll bring this down for a second. Using the classes over here on the left, if you use those classes, this is the picture that you get for this particular set of data. Now, if you look at this for a moment, you can kind of see that it's not a perfect bell shape. It's not perfect, but it's pretty close. It's pretty much a bell-shaped distribution. You have this sort of single peak, data is symmetric on either side of it, and we get sort of a almost bell-shaped distribution. Okay? If we go through and we calculate the mean for this collection of data is about 39. And the standard deviation ends up being somewhere in the neighborhood of 13.2. If we go back and look at the raw data again, and I cannot fit this all on a page very well. Let's see if I can get. Can you see all that? See the numbers there? No? All right. Blow it up a little bit better. The data looks. Again, here's sort of the distribution of values down this first side here. And all I did is I went ahead and I ordered them from least to greatest. Now, one thing you'll notice is that all of these values have a different color associated with them. And that color serves to represent certain aspects of our distribution. Go back to our picture here. Actually, I'm going to draw a picture up here on the board in a second. So we'll come away from this for just a moment. That bell-shaped distribution, we'll go back to that for just a moment. Put away a picture. Our picture that we had for our football data looked something like this. We had a little block down here, a slightly higher block here, our biggest one in the middle, slightly smaller on the other side, another slightly smaller one. And then our very smallest one right here. Okay? Our mean was somewhere in this category. It was equal to 39. Okay? And our standard deviation for this one was 13.2. Now, interestingly enough, this allows us to identify certain percentages in terms of how much data falls within certain aspects of our picture here. Okay? If we were to take our standard deviation here, if we were to take our x bar and we were to add one standard deviation to it, so you take x bar plus s, do the addition there, that ends up being 52.2. And at the same time, we're going to subtract one standard deviation. Subtracting one standard deviation from that gives us, okay. Now, if we look at the data, if we go back to that raw data that we had, that big list of numbers, what you would find, and I'll do this so that you don't have to. Remember, there were 119 football teams. If we look at how many teams fall within these categories, so 119 total, 58 of our, 81, long call. 81 of the teams fall within these two values. 81 values between 52.2 and 25.8. As a percentage, what is that? If you were to calculate that as a percentage, what would you get? 68. I don't think you did exactly that. Yes, you're close. In this case, we actually get 68. Oh. Man, it's amazing how things work out like that. All right, so it turns out that 68% of our data values fall within one standard deviation of the mean. That is not a coincidence. Okay? That's not a coincidence. When dealing with bell-shaped distributions like this, this is one of the rules that all bell-shaped distributions follow. Is that if you have a bell-shaped distribution, 68% of all of your data, or approximately 68% of all of your data, is going to be within one standard deviation of the mean. Okay? This rule is what is known as the empirical rule. There are three parts to it. So you have a bell-shaped distribution. Part 1 says that 68% of all data is within one standard deviation of the mean. Okay? When I say within one standard deviation, what that means is that if I go below one standard deviation, if I take my mean and I go down one standard deviation, and I take my mean and I go above one standard deviation, okay? Within one standard deviation means you might be one standard deviation lower or one standard deviation higher, but 68% of all of my data is going to be within one standard deviation of our mean. Okay? Our picture here, 25.8 there, 52.5 or 52.2 would go approximately there. Okay? And so what it's saying is that if we were to cut off all of our data and just look at the stuff in that one box that I have there, the amount of data that shows up in that box is 68%. Okay? All right. Now, what if we go out one more standard deviation? What if we go one more standard deviation on the low side and one more standard deviation on the high side? Well, 2. Well, let's see. If we count how much is on that side, what we end up with is, let's calculate the range first, the range of those two standard deviations below, 2 standard deviations above. If we take x bar plus 2 standard deviations, what do we get? That's right, we get 65.4. Good job. Okay. And then if we go lower, x bar minus 2 standard deviations, what do we get there? 12.6. There you go. 12.6 on the low side. All right, good job. Okay. And if we look and see how many teams fall within this category, well, there are 117 teams. 117 teams whose touchdown totals are between the 65.4 and the 12.6. Okay? So percentage-wise, let's see, that's 98 exactly. Close. Ends up being 98.3. But in terms of what our rule says, our rule doesn't say 98.3%. Our rule actually says 95% of all data is within 2 standard deviations of the mean. Okay. Again, these are approximations. It's our graph over there is not a perfect bell shape. It's approximately bell shaped. So in terms of our rules here, we're not going to get exactly 95%, but we're getting approximately 95%. In this case, our approximation is a little high, but that's all right. It's still there. Okay? All right, so that's the second part of the rule. There's one final part to the rule. The final part of the rule says go 3 standard deviations out. Okay? 3 standard deviations out from your mean. What do you expect to happen there? Well, in our case, if we go 3 standard deviations, x bar plus 3s and x bar minus 3s. So let's see, x bar plus 3s, I raised for standard deviation, 13.2. X bar was 58. If we go 3 standard deviations out, well, let's see, that's just another, add 13.2 to this, what do we get? Okay, and then add or subtract another 13.2 from here, and you get a negative value.
0.
We're just going to call it 0 for now, because the numbers that we get out here have to have real meaning. I can't score negative touchdowns. Safeties don't count as negative touchdowns. So we'll use a 0 there. Okay? If we look at our data now, 118 out of 119 fall within this category. All but one of our teams falls within this range of scores. Okay? As a percentage, that's 99 point something 6. 7 new. Let's see. 99.2. Sorry. Okay. But basically, if we look at this value here, almost every single data value that we have falls within this range. That's what the third part of the rule says. Part 3 says that 99.7% or almost all data is within 3 standard deviations of the mean. Okay? And that's a good tool because being able to identify this, being able to identify that we can use the empirical rule gives us a little bit more information about our distribution. We can describe it a little bit more. We have a little bit more things that we can put into our story about what our data is telling us. All right? So if we look at another example, I want to leave as much of this up here as I can. Does everyone have all this written down, Wilson? Everything they want to write down? Thank you. All right, so as an example, ACT verbal scores are distributed approximately bell-shaped. With a mean of 21 and a standard deviation of 6. Okay. Here's some questions that I would like to have answers to. The first one, what % of students